Welcome, AXOR, Galactic Observatory. Tonight, the journey moves to the nearest great stellar neighbour beyond our Sun, where a possible world around Alpha Centauri A appears, vanishes, and leaves astronomers facing one of the most fascinating mysteries in modern space science. In this calm and carefully told documentary, the story follows the James Webb Space Telescope, the search for a lost Saturn-mass planet, the scientific debate over whether it was ever truly there, and what this strange case could mean for the future of exoplanet discovery and humanity's first interstellar destination. As the mystery unfolds, the deeper wonder of the universe comes quietly into view, revealing how science advances through patience, uncertainty, and the faintest traces of light in the dark. Before settling in, please like the video, subscribe to the channel, and support AXOR, Galactic Observatory, for more relaxing journeys through the deepest mysteries of space. Alpha Centauri rests in the sky as a familiar point of light, calm and ordinary to the eye, yet in astronomy it holds a place unlike any other star system beyond the Sun. It is the nearest stellar system to Earth, a small neighbouring archipelago of suns suspended just over 4 light-years away, close enough that its light crosses the gulf of interstellar space in a span shorter than a child's years in school, and close enough that even the vast distances between stars begin, for a moment, to feel measurable. In the language of astronomy, 4 light-years still means an almost unimaginable separation, roughly 25 trillion miles, a distance so great that the fastest spacecraft ever launched by humanity would need many thousands of years to arrive. Yet compared with every other Sun-like system studied in the search for other worlds, Alpha Centauri is next door. That simple fact changes everything. A world around a distant star can be a scientific treasure, a data point in a growing cosmic census. A world around Alpha Centauri can become something more. It can become a destination in waiting, a place that lives not only in equations and telescope images, but also in plans, in engineering studies, and in the long imagination of a species that has only just begun to leave its homeworld. This is why the system exerts such a steady pull on astronomers, mission designers, and anyone who looks at the night sky and wonders where humanity might someday go. It is not merely nearby in a technical sense. It is nearby in a psychological sense. It stands at the edge of what feels unreachable and what might one day, with enough time and patience, enter the realm of the possible. The importance of Alpha Centauri begins there, with proximity itself. Distance shapes all of astronomy. The farther an object lies from Earth, the fainter it appears, the smaller it seems, and the less detail can be recovered from the light it sends. Nearness changes the quality of knowledge. A nearby star can be measured more precisely, its motion traced more carefully, its brightness studied more deeply, its surrounding environment searched with greater sensitivity. The same telescope that sees only a hint of a planet around a star many dozens of light-years away may, when pointed toward Alpha Centauri, reach into a finer level of detail. The system becomes a testing ground for the limits of observation. It invites astronomers to ask not only whether planets exist there, but what kinds of planets, at what distances, with what masses, with what atmospheres, with what histories. Every improvement in technology makes the system newly urgent. Better instruments do not simply add one more target to the list. They return, again and again, to this nearest neighbour because the reward for success there is uniquely large. In a catalogue of thousands of known worlds, a planet around Alpha Centauri would not be important because it is the largest, or the strangest, or the most extreme. It would be important because it would be the closest example of another planetary home beyond the solar system, the nearest place where the general story of exoplanets becomes intimate. The search for such a world is therefore scientific, but it is also deeply human. It folds together precision and longing, measurement and possibility. That tension gives the Alpha Centauri system its unusual emotional weight within modern astronomy. For centuries, nearby stars have inspired speculation, but most remained abstract. They were bright points in the dark with unknown distances and unknowable worlds. Modern astronomy changes that. It measures parallax, the tiny apparent shift in a star's position caused by Earth moving around the Sun, and from that shift it derives distance with extraordinary care. It measures radial motion, the movement of a star toward or away from Earth, by tracking how starlight is stretched or compressed. It measures proper motion, the slow drift of a star across the sky over years and decades. In Alpha Centauri, all of these motions are especially clear because the system is so near. The stars are not frozen lights, they are moving neighbours, members of the same larger galactic city as the Sun, passing through the Milky Way on their own long path. That motion reinforces the sense that this system belongs to the local landscape of space, rather than to some remote and unreachable background. For this reason, Alpha Centauri has long served as a symbolic threshold. Beyond the Moon lies the solar system. Beyond the solar system, for the human imagination, lies Alpha Centauri. When discussions turn to interstellar travel, its name appears almost immediately. Not because it is easy to reach, but because every other candidate is farther. In that hierarchy of difficulty, the nearest star becomes the first practical dream. Concepts such as laser-driven sailcraft, miniature probes accelerated to a fraction of the speed of light, and long-term robotic exploration are often framed with Alpha Centauri in mind. Even when such missions remain speculative, the choice of target reveals how central the system has become in thinking about the future. A confirmed planet there would sharpen those ideas overnight. It would turn a nearby star into a nearby world. It would transform a destination of principle into a destination with geography, orbit, and physical character. Even a gas giant, not itself a place for human settlement, would matter greatly because gas giants often indicate broader planetary architecture. Their presence can hint at inner rocky planets, stable orbital zones, and a richer history of formation. Thus, the stakes surrounding any claimed planet in this system rise well beyond the normal excitement of exoplanet discovery. They touch on the oldest astronomical question in a new and concrete way. Are there other worlds near enough to become part of humanity's actual future, not just its philosophy? That is why Alpha Centauri matters before any particular planet is discussed. It matters before the instruments, before the data processing, before the debate over what was seen and what later seemed to vanish. The system itself carries the weight. Its light reaches Earth from the nearest shore beyond the Sun. Its distance is still enormous, but not anonymous. Its stars mark the first outward step in the map of interstellar ambition. And somewhere within that nearness lies the reason every possible planet there feels larger than itself, carrying the gravity not only of mass and orbit, but of hope. The Alpha Centauri system is not a single star, but a small family of three, bound together by gravity across distances that are vast in human terms, and yet intimate by the standards of the galaxy. At its centre are Alpha Centauri A and Alpha Centauri B, a close binary pair that circle one another in a slow and elegant orbital rhythm. Farther away lies Proxima Centauri, a dim red dwarf that drifts on the outer edge of the system, loosely attached to the brighter pair and following its own much longer path. To understand why any possible planet around Alpha Centauri matters so much, it helps to begin with the stars themselves, because planets do not form in isolation. They emerge from the conditions created by their parent stars, and in a multiple star system those conditions are shaped by companionship as much as by solitude. Alpha Centauri A is the brightest and most massive of the main pair. It is often described as a near twin of the Sun, though not a perfect one. Its mass is slightly greater, its luminosity somewhat higher, and its surface temperature just a little warmer. In spectral class, it belongs to the same broad family of yellow-white stars that includes the Sun, and for that reason it has long attracted interest as the kind of star around which familiar forms of planetary architecture might arise. Alpha Centauri B is smaller, cooler, and somewhat dimmer. An orange star that still burns steadily but with less energy. The two stars orbit a shared centre of mass in a stretched ellipse, sometimes drawing relatively near and at other times moving much farther apart. Their average separation is often compared with the distance between the Sun and the outer planets of the solar system, though the exact gap changes over the course of their orbit. This changing separation matters because it affects the gravitational environment in which planets must survive. A binary system is not an impossible place for planets. The galaxy has already shown that planets can exist in many arrangements, including around stars that travel with companions. Yet the presence of a second star can influence how disks of gas and dust evolve during planet formation, how stable certain orbits remain over long spans of time, and how much light and heat planets receive. The Alpha Centauri pair therefore represents both promise and complication. It offers stars that seem familiar, but sets them within a gravitational partnership that must be taken seriously. Their orbital period around one another lasts roughly 80 years, which means the movement of the pair unfolds slowly enough to be followed over a lifetime of careful observation. Astronomers have traced that motion with extraordinary precision, turning the system into one of the best measured stellar laboratories in the sky. From those measurements come reliable estimates of mass, distance, and geometry, all of which shape the expectations for where planets could reside safely. Around each of the two main stars there is a region close enough that a planet can orbit one star without being torn away by the other. In those inner zones, stable planetary orbits are considered possible over very long periods. Beyond that, at larger distances from either star, the tug of the companion grows stronger and the structure of allowed orbits becomes less simple. In this way, the architecture of the system is layered, with certain neighbourhoods offering long-term calm and others carrying more dynamical tension. For Alpha Centauri A, that stability zone includes the region where temperate rocky planets might exist, but it can also include wider paths for giant planets, depending on the exact orbital configuration. This is one reason the search there has remained scientifically credible for so long. The presence of a stellar companion does not erase the possibility of planets. It frames the search in more detailed terms. Proxima Centauri, the third member of the system, deepens that complexity while also adding contrast. Unlike the brighter central pair, Proxima is a red dwarf, much smaller, much cooler, and vastly fainter. It lies thousands of times farther from Alpha Centauri A and B than they lie from one another, so far away that if a planet orbited Alpha Centauri A, Proxima would scarcely brighten its sky. Yet gravitationally it appears to belong to the same broader system, moving through space in a related way and sharing a common neighbourhood over immense stretches of time. Proxima has already been shown to host planets, including at least one world roughly Earth-sized, though its environment is very different from that of the Sun or Alpha Centauri A. As a red dwarf, it is prone to flares and energetic outbursts, and its habitable zone lies much closer to the star. This contrast makes the brighter pair even more compelling. If Proxima represents one path of planetary possibility, Alpha Centauri A and B represent another, more sun-like path, one that feels easier to compare with the solar system, and perhaps easier to imagine as a future destination. The three stars together create a layered local cosmos, two bright stars in a close dance, one dim companion lingering at the system's edge. Their long companionship is not static. Over millions of years, the stars travel through the Milky Way while maintaining their bond. And within that shared motion lies the deep timescale on which planets form and survive. A protoplanetary disk around Alpha Centauri A in the distant past would not have developed under the same conditions as the disk that once surrounded the young Sun. The light from Alpha Centauri B would have been present in the sky. Its gravity would have subtly shaped the outer regions of the disk. Collisions among growing planetesimals, or small bodies that merge to become planets, may have occurred under slightly altered velocities and patterns, yet altered does not mean prevented. Numerical studies over the years have shown that planets can arise in such environments, especially in the inner stable zones, though the details depend on assumptions about disk mass, eccentricity, and early migration. In this sense, the Alpha Centauri system stands between familiarity and difference. Its stars are close enough to the Sun in character to feel almost recognizable, yet the binary arrangement ensures that its history cannot simply be copied from our own. That tension is part of the system's appeal. It is local but not identical, nearby but not simple. To look at Alpha Centauri is to look at a version of stellar companionship that broadens the meaning of what a planetary home might be. The stars move around one another with no awareness of the hopes placed upon them. Their orbital dance continues whether or not a planet is ever confirmed in their light. But that dance sets the stage for everything that follows. It defines the gravitational background, the illumination, the possible safe harbours for orbiting worlds, and the outer limits of stability. In astronomy, structure always comes first. Before a world can be imagined, the stars must be understood. And in Alpha Centauri, those stars form not a single beacon, but a system of relationships. Luminous bodies tracing a shared geometry whose quiet motion has become one of the most closely watched arrangements in the sky. For astronomers, the importance of worlds around Alpha Centauri does not rest only on distance, though distance is the first and most obvious reason. A nearby planet matters because nearness makes every scientific question sharper. It brings the possibility of a world out of the statistical background and into a domain where its nature may eventually be studied in detail. In most exoplanet systems, the known planets remain remote presences, identified through faint periodic signals, slight dips in starlight, or tiny motions of the host star. Their existence can be measured, their masses estimated, their radii constrained, and in a few fortunate cases some glimpse of atmospheric chemistry can be obtained. Yet for all that progress, many exoplanets remain abstractions, distant enough that the imagination must work harder than the telescope. Alpha Centauri changes the scale of that relationship. A planet there would still be beyond present travel, still unattainable by any current spacecraft, yet it would feel anchored in a different category of reality. It would not merely belong to the galaxy at large, it would belong to the local stellar neighbourhood, a world close enough to become the focus of generations of increasingly refined observations. This is why astronomers have searched the system so persistently. The search is not driven by romance alone, though romance is never entirely absent from astronomy. It is driven by the recognition that a planet around Alpha Centauri would offer the richest possible target for the future of exoplanet science. A nearby world permits better measurement of orbit, better constraints on mass, greater opportunity for repeated observations, and a stronger chance that future instruments might isolate its light from the glare of its star. Even small improvements in telescope design or data processing would pay large dividends there, because the system begins from such an advantageous position. In a nearby system, the apparent separation between star and planet on the sky can be wider than in a more distant system with the same actual orbital distance. making direct imaging somewhat less hopeless. A nearby star is also brighter, which can help certain measurements even as it creates new challenges through overwhelming glare. Thus, Alpha Centauri exists in a rare observational balance, difficult but tantalizing, close enough to encourage bold efforts, bright enough to reward precision, and important enough to justify repeated campaigns over many years. The scientific value of a planet there also depends on what such a planet could reveal about planetary formation under familiar but not identical conditions. Alpha Centauri A, with its sun-like character, invites comparisons with the solar system that few other nearby stars can match. If a giant planet were found around it, astronomers would ask how such a world formed in a binary environment, how migration may have shaped its orbit, and whether smaller rocky planets might share the system. If a terrestrial planet were found, especially in a temperate orbit, the significance would grow still further. The system could become a benchmark for theories of habitability, atmospheric evolution, and planetary architecture around sun-like stars with stellar companions. In that sense, even one confirmed planet would become more than one object. It would become a clue to an entire hidden arrangement. This logic explains why a gas giant can matter even when the longings of the public often focus on Earth-like worlds. In planetary systems, giant planets can be signposts. Their presence can indicate that planet formation was robust, that enough material existed in the primordial disk to build large bodies, and that the system may contain a broader family of worlds still awaiting detection. In the solar system, the giant planets help define the architecture of the whole. They influence the movement of comets, the delivery of material, and the long-term stability of smaller worlds. Something similar could hold true around Alpha Centauri A. A Saturn-mass planet would not itself be habitable in the ordinary sense, yet it might possess moons, rings, weather systems, and a formation history that speaks to the wider planetary past of the system. It would also show that the nearest sun-like star has indeed made planets, turning a long-standing question into a foundation for many others. Beyond science, nearby worlds matter because they alter the horizon of planning. Human civilization has not yet crossed interstellar space, and no present technology can send a large spacecraft to Alpha Centauri within a human lifetime. That limitation is real and severe. Yet there is a meaningful difference between discussing interstellar travel in the abstract and discussing it in relation to a specific world orbiting a specific nearby star. A confirmed planet provides focus. It gives propulsion studies a target. It gives instrument designers a reason to define future missions around known orbital phases and likely brightness ranges. It gives public imagination something firmer than a point of light. In the history of exploration, maps change behavior. Even a rough chart can redirect energy, money, and attention. In astronomy, a planet around Alpha Centauri would function as that kind of map. Not a map for immediate travel, but a map for serious intent. This is why conversations about interstellar probes so often mention the system. The nearest stars are not all equally compelling. Proximity helps, but familiarity of stellar type also matters, and Alpha Centauri A combines both. It resembles the Sun enough to stir comparison, yet differs enough to remain scientifically fresh. That combination makes it the first destination that feels both alien and legible. It belongs to the same universe as Earth in a particularly direct way. The nearby worlds of such a star would not simply expand the inventory of exoplanets, they would alter the mental geography of humanity's future. Astronomers know, of course, that desire cannot substitute for data. A system may be beloved and still be empty of detectable planets, or filled with worlds that are difficult to observe. The sky does not arrange itself according to human hope, but hope still influences where attention gathers, and Alpha Centauri has gathered attention for decades because it concentrates so many lines of value into one place. It is near, it is bright, it is structured in a way that tests theories of formation and stability. It contains a star that resembles the Sun. It lies at the threshold where exoplanet science touches the dream of interstellar reach. All of this means that when a possible signal appears there, the response is never ordinary. Every candidate planet immediately carries more weight than its own mass. It becomes a vessel for questions that began long before the observation itself. Could the nearest Sun-like system host worlds? Could those worlds be studied in detail? Could one of them someday become the target of the first true journey between the stars? These questions remain unresolved, but their power explains why Alpha Centauri has never been just another exoplanet search field. It is the first outward circle beyond the solar system where discovery begins to feel personal, and where even the faintest hint of a world can seem to pull the future a little closer. Seeing a planet around another star is difficult not because planets are rare, but because stars dominate almost everything around them. A star pours out light in overwhelming abundance, while a planet shines weakly by comparison, usually reflecting starlight or releasing only a modest glow of its own heat. From far away, this imbalance becomes severe. The planet is not only much fainter than the star, but also appears extremely close to it on the sky. The problem is therefore double. First, astronomers must distinguish a dim source from one that is many thousands, millions, or even billions of times brighter. Second, they must do so at a separation so small that the light of the star spreads into the region where the planet would appear. Even with excellent telescopes, the star's glare does not stay politely confined to a single point. Light diffracts, meaning it bends and spreads in patterned ways as it passes through an optical system. Tiny imperfections in mirrors, small thermal shifts, detector noise, and subtle vibrations can all produce scattered light and false structures in an image. These effects create a background that is bright, uneven, and treacherous, especially near the star itself. A real planet must be found within that difficult terrain, where the eye easily sees shapes that are not worlds, and where processing methods, though powerful, can sometimes generate misleading features. This challenge defines much of modern exoplanet astronomy. The planets are there, but they are buried in light. Astronomers therefore rely on several different methods to detect them, each designed to infer the presence of a planet without always seeing it directly. One common method is the transit technique, in which a planet passes in front of its star from Earth's point of view and causes a tiny drop in brightness. Another is the radial velocity method, which measures the small back and forth motion of a star as an orbiting planet pulls on it through gravity. There is also astrometry, which tracks minute changes in the position of a star on the sky, and microlensing, which depends on the way gravity bends light from a more distant background source. Direct imaging, the method most relevant to a case like Alpha Centauri A, attempts something harder and more visually intuitive. It tries to isolate the light from the planet itself. This can mean reflected light in visible wavelengths or thermal emission in infrared wavelengths, depending on the planet's temperature, age, and atmospheric properties. Direct imaging is powerful because it can, in principle, provide information about the planet's brightness, colour, temperature, orbit, and perhaps even atmospheric composition, but it works best for planets that are either far from their stars in apparent separation, relatively young and warm, or both. A nearby bright star with a faint planet close to it remains one of the hardest targets in astronomy. Alpha Centauri A is especially challenging for reasons that arise from its strengths as well as its weaknesses. Its nearness is an advantage because nearby systems place a larger angular separation between star and planet, than more distant systems with the same physical layout. In other words, a planet orbiting at a given distance from Alpha Centauri. It may appear a little farther from the star in the image than a similar planet around a much more distant star. That helps. But the star is also extremely bright, and brightness produces glare, saturation risk, scattered light, and strong diffraction patterns. The telescope is asked to examine a dim companion almost pressed against a beacon. This is like searching for a faint ember beside a flood lamp, while the optics themselves scatter some of the flood lamp's light across the field. The closer the suspected planet lies to the star, the more severe this contrast problem becomes. Around Alpha Centauri A, the search is not just for something faint. It is for something faint in one of the most optically unforgiving neighbourhoods a telescope can face. The binary nature of the system adds another layer of difficulty. Alpha Centauri B, though not always close in the field of view, is still a luminous companion star in the same broader system. Depending on the observing configuration, its presence can complicate interpretation, observational planning, and expectations for planetary stability. More generally, the entire search around Alpha Centauri unfolds in a context where high precision is mandatory. Small errors in calibration matter, slight mismatches between telescope orientations matter, detector artifacts matter, background subtraction matters, image processing choices matter. In many astronomical settings, imperfections can be tolerated because the signal is strong. Here the signal is expected to be marginal, and marginal signals are shaped by every part of the method. This is why exoplanet imaging near bright stars often involves elaborate observational strategies. Astronomers take images at different telescope roll angles, meaning the telescope is rotated so that real astrophysical sources move in a predictable way on the detector, while some instrumental artifacts remain fixed. They compare wavelengths because planets and scattered starlight behave differently across the spectrum. They build models of the point spread function, the detailed pattern a point source of light forms in the optical system, and subtract that model from the image to remove as much stellar contamination as possible. They search not only for bright spots, but for bright spots that persist in the right way across different conditions. The more convincing a candidate appears under these tests, the more likely it is to represent something real. Yet even then, certainty can remain elusive, because the search is happening at the frontier of instrumental capability. Alpha Centauri therefore becomes a special kind of challenge. It is attractive enough to justify the most advanced efforts, but difficult enough that any apparent success must survive exceptional scrutiny. A candidate there cannot be treated like an ordinary detection. It must answer a harder question: is this point of light actually a planet? Or is it some interaction between glare, noise, dust, processing, and wishful interpretation? Astronomy has learned this caution through long experience. The history of planet hunting includes premature claims, statistical ambiguities, and signals that faded under better data. That history does not make discovery impossible. It makes discipline essential. A world near Alpha Centauri A would be one of the most consequential planetary detections imaginable, and that consequence raises the standard of proof. The irony is quiet but important. The nearest promising system is not automatically the easiest place to find a planet. In some ways it is harder, because a nearby bright star demands exquisite control over light itself. The planet, if present, may be close enough to matter profoundly, and still remain hidden inside the optical weather of the star. This is the central difficulty that shapes the entire story. Before any point of light can become a world, astronomers must first learn how to look through brilliance without being deceived by it. The James Webb Space Telescope enters this story not as a general symbol of advanced astronomy, but as a specific instrument built to work where faint heat can be separated from overwhelming glare. Its power lies partly in size, partly in stability, and partly in the wavelengths of light it observes. With a segmented primary mirror spanning more than 6 meters, it collects far more light than earlier space telescopes operating in similar regions of the spectrum. More importantly, for a search like the one around Alpha Centauri A, it is designed primarily for infrared astronomy. Infrared light lies beyond the red end of the visible spectrum, and in that range many objects that seem dim to human eyes reveal a different kind of presence. Warm dust glows there. Cooling planets emit there. Atmospheric molecules leave distinctive patterns there. A planet that is almost invisible in visible light may become more accessible in infrared if it still holds enough internal heat, or if its atmosphere radiates efficiently at certain wavelengths. This is why infrared astronomy has become such a vital pathway in the study of planets beyond the solar system. It does not erase the contrast problem between star and planet, but it can shift the balance enough to make detection more plausible. A star like Alpha Centauri A still shines strongly in infrared, yet a giant planet may contribute a more meaningful fraction of light there than it would in visible wavelengths. That modest advantage can be decisive when combined with careful optical suppression. Webb also benefits from its location in space. Earth's atmosphere is both protective and troublesome. It shields life from harmful radiation, but for astronomy it blurs and brightens the sky. Turbulence in the atmosphere distorts incoming starlight, producing the familiar twinkling of stars and complicating any effort to resolve extremely fine detail. Water vapor and other gases absorb parts of the infrared spectrum, limiting what ground-based telescopes can see. Modern observatories use adaptive optics to correct some of the atmospheric distortion, and they can achieve remarkable results. But a telescope above the atmosphere begins with a quieter image. Webb orbits far from Earth near the second Sun-Earth Lagrange point, where it can remain cold, stable, and continuously shaded by its large sun shield. That cold environment matters because a warm telescope would glow in infrared and contaminate its own measurements. Webb is therefore not only large and sensitive, it is thermally disciplined. Its instruments are kept at low temperatures so that the faint infrared signals from distant objects are not drowned by the telescope's own emission. In a search for a weak planetary glow near a bright nearby star, this discipline becomes essential. The telescope must not add unnecessary light to an already difficult scene. Among Webb's instruments, the one most relevant to this part of the story is the mid-infrared instrument, often called MIRI. This instrument observes at longer infrared wavelengths than the near-infrared cameras and spectrographs aboard the telescope. In the mid-infrared, warm giant planets and circumstellar dust can become especially interesting, because their thermal emission can stand out more clearly. MIRI also includes coronagraphs, specialized optical elements designed to suppress the light of a star so that faint nearby material can be studied. A coronagraph does not remove starlight completely. It reduces its most concentrated central glare and reshapes the field enough that dim companions may emerge from beneath the star's overwhelming brightness. The principle is simple in concept and demanding in practice. Part of the starlight is blocked or redirected, while the surrounding image is analysed with extreme care. Because no optical system is perfect, residual structures remain, and those structures must be understood through calibration, modelling, and comparison across observing geometries. Yet without a coronagraph, some searches would remain hopeless. It is one of the main tools that allows a telescope like Webb to move from seeing stars alone to searching for worlds and dust around them. Around Alpha Centauri A, the telescope's capabilities align almost exactly with the requirements of the problem. The star is close, bright, and difficult. A candidate giant planet there, especially one with some retained warmth, may be accessible in mid-infrared as a faint thermal source. At the same time, the star's brilliance requires suppression strong enough to reveal anything nearby. Webb is not the first telescope to confront such a challenge, but it represents a major step in sensitivity and stability. Previous space telescopes made transformative contributions to exoplanet science, especially through transits and atmospheric studies, while powerful ground-based systems push direct imaging forward with adaptive optics. Webb joins this history as an instrument capable of working at the delicate boundary between glare and faint heat in a way that earlier tools could not fully match. This is why hopes became concentrated around it even before specific results were announced. It offered not certainty, but a new regime of possibility. Astronomers knew that Alpha Centauri would remain difficult. Yet difficulty is not fixed. It changes when instruments change. A system that once yielded only upper limits and ambiguous hints could, under the right conditions, begin to show structure. Webb's design therefore altered the emotional landscape of the search. The nearest Sun-like system was no longer only a future target for larger missions. It was becoming a present target for a telescope already in operation. There is a quiet elegance in the way the observatory approaches such work. It does not stare with brute force alone. It uses wavelength choice, thermal control, optical suppression, and stable imaging to create conditions where subtle signals may survive. Even its observing strategies reflect this philosophy. Images can be taken at different orientations so that real celestial sources rotate with the field, while some instrumental features remain fixed relative to the detector. Multiple filters can probe how brightness changes with wavelength, helping astronomers distinguish a warm object from scattered starlight or detector artifacts. Repeated processing methods can test whether a point of light is stable under different assumptions. All of this extends the telescope beyond simple seeing. It becomes a machine for separating possibilities. In the case of Alpha Centauri A, that capacity is especially valuable because the question is not only whether something is present, but whether what appears in the data deserves belief. Webb provides the means to ask that question at a higher level than before. It does not guarantee a planet. It provides a new way to interrogate light itself, to ask whether hidden heat, buried near brilliance, can be coaxed into view. That is the threshold the telescope opens. In the darkness beyond visible sight, where planets shine not by reflected sparkle alone, but by their own muted warmth. Webb creates a narrow path through which a neighbouring world might briefly become visible. The first dedicated Webb search around Alpha Centauri A unfolds as an exercise in patience shaped by precision. Before any candidate world can be discussed, the observation itself must be understood as a carefully staged encounter between instrument and target. Astronomers do not simply point a powerful telescope at a bright nearby star and wait for a planet to appear. They build a strategy around the known weaknesses of the problem. They consider how the star's light will spread through the optics, how the detector will respond, how faint sources might be confused with residual glare, and how the geometry of the observation can be used to separate reality from illusion. In the case of Alpha Centauri A, these concerns are especially intense because the system is both attractive and punishing. It offers perhaps the most tantalizing nearby sun-like star, but it also confronts Webb with a scene dominated by light that must be suppressed, modelled, and questioned at every stage. The observing campaign is therefore designed not only to collect photons, but to create comparison, redundancy, and movement within the data. One of the most important ideas behind the strategy is that a real astronomical source behaves differently from many instrumental artifacts when the telescope changes orientation. Webb can observe the same field at different roll angles, meaning the telescope is rotated relative to the sky. When that happens, an actual object in orbit around Alpha Centauri A maintains its place in the sky, and therefore appears at a rotated location on the detector, while certain patterns caused by the instrument itself remain fixed relative to the telescope. This distinction becomes a powerful test. If a faint point of light seems to move in the way a real sky source should when the telescope rolls, it gains credibility. If it remains locked to a detector feature, it loses it. The search therefore builds in this geometric leverage from the start. It is a method of making the universe and the instrument part ways under controlled conditions. The target is also observed in more than one wavelength band, especially in the mid-infrared where a warm giant planet may emit detectable thermal radiation. A true planetary candidate should show behavior across wavelengths that makes physical sense. Its brightness should not vary in arbitrary ways from filter to filter. Instead, it should roughly align with expectations for a cool or warm atmospheric emitter, even if those expectations carry uncertainty, dust, detector noise, and residual starlight can each produce their own spectral signatures, or sometimes no stable pattern at all. By comparing images taken through different filters, astronomers gain another way to judge whether a faint feature belongs to the sky or to the machinery of observation. In practice, this process is never as clean as the concept suggests. Real data arrive burdened with imperfections. Bright stars produce extended structures in the image. Subtraction methods can create both false positives and false negatives. A source that looks persuasive in one pass of processing may weaken in another. For this reason, the observing campaign is tied from the beginning to a demanding program of data reduction, calibration, and cross-checking. The raw image is only the beginning. Once the observations are taken, the harder work begins. The star's glare must be modelled and removed as effectively as possible, without erasing a real source nearby. This usually involves constructing representations of the stellar point spread function and comparing images across orientations and wavelengths. Small shifts in alignment matter. Small mismatches in intensity matter, because the suspected planetary signal lies near the threshold of visibility. The final result depends on the quality of these reductions. The observing strategy is therefore inseparable from the reduction strategy. They are two halves of the same attempt to make something faint survive. Timing also matters in subtle ways. A search around Alpha Centauri A is not performed in an abstract vacuum. The stars themselves move. The telescope's observing windows are constrained by spacecraft operations, and follow-up plans depend on what the first epoch reveals. The initial Webb campaign is best understood as a first pass through a narrow gate. It seeks not complete certainty, but enough information to determine whether there is something worth deeper scrutiny. In many exoplanet searches, this first pass ends quietly, with non-detections that still improve upper limits and refine future strategies. Around Alpha Centauri A, however, even the possibility of a faint unresolved source carries unusual weight, because the target is so important, and the expectations surrounding Webb are so high. This means that the first search is conducted within an atmosphere of disciplined hope. The astronomers involved understand the temptation of over-interpretation, and yet they also know that the instrument has opened a new observational regime. Something that was previously hidden may now, for the first time, sit just within reach. The field itself can include more than a possible planet. Infrared observations may also reveal dust structures, background objects, or circumstellar material, all of which must be distinguished from the hoped-for prize. A distant background galaxy, for example, can appear as a small point or compact source if the resolution and brightness align in the right way. Dust within the Alpha Centauri system, warmed by starlight, can contribute infrared emission with shapes and intensities that complicate interpretation. The observational plan therefore does not assume a simple scene. It assumes a contested one. every point of light is a question before it is a world. In this sense, the first Webb search around Alpha Centauri A is not a single act of looking, but a sequence of tests built into the act of looking itself. Orientation, wavelength, suppression, subtraction, and later comparison are all present from the beginning as parts of one methodological fabric. The telescope is not merely gathering a picture, it is creating a framework in which faint structures can be interrogated. That framework matters because the history of difficult detections in astronomy teaches a quiet lesson. The most exciting claims are often born at the edge where method is most vulnerable. To work at that edge responsibly, the observing campaign must be designed so that a true source has several ways to prove itself. By the end of the first Webb search, what exists is not yet a planet or a refutation, but a carefully prepared field of evidence. The bright nearest sun-like star has been challenged in infrared light with one of humanity's finest instruments. The glare has been pushed back as far as current methods allow. The image has been made to rotate, to split by wavelength, to yield to subtraction. And within that prepared darkness, something may or may not be beginning to stand out. In difficult observations, there is rarely a single moment when a planet simply appears in full clarity. What emerges first is usually more fragile than that. A small persistence in the data that survives one test and then another. A point of light that refuses to vanish when the image is rotated, filtered, or reduced under slightly different assumptions. In the Webb observations of Alpha Centauri A, the candidate object enters the scientific story in this quieter way. It is not a dramatic visual revelation, not a bright companion standing free of the star, but a faint localized source detected in processed mid-infrared images after the strongest stellar glare has been suppressed and the remaining structures examined with care. Its importance lies not in immediate certainty, but in the fact that it occupies the kind of position and brightness range where a planetary interpretation cannot be dismissed at once. This is the stage in astronomy where caution and excitement begin to overlap. A faint source near a star like Alpha Centauri A must earn belief gradually. Its first duty is persistence. If the point of light appears only in one reduction path and disappears in another equally reasonable one, confidence weakens. If it remains visible after different approaches to subtraction, or after small adjustments in alignment and calibration, then it becomes harder to explain away as a transient artifact of processing. The initial candidate seems to pass enough of these early tests to justify deeper attention. It is seen near the star at a separation consistent with a possible bound companion, rather than at some obviously distant location. It does not immediately identify itself as a simple diffraction spike, detect a blemish, or known instrumental ghost. More importantly, when the telescope orientation changes, the source behaves in a way more consistent with a feature on the sky than with a feature locked to the instrument. This is not proof, but it is the kind of evidence astronomers are trained to respect. A source that rotates with the field begins to step out of the category of mere nuisance and into the narrower, more consequential category of candidate. The word candidate matters here. Astronomy uses it not as a formality, but as a protective boundary between appearance and conclusion. The point of light is real in the sense that something has been measured in the image at that location. But what that something represents remains open. It could be a planet, it could be dust, it could be a background source, it could be an interaction between several subtle effects not yet fully separated. The first appearance of such a source does not collapse these possibilities, it reorganizes them before the signal is found. The hypothesis of a planet is a general hope. After the signal is found, the hypothesis becomes a specific claim tied to one position, one brightness, and one set of observational circumstances. That transition is crucial. It allows the scientific discussion to move from broad possibility to concrete testing. The candidate can now be measured. Its projected separation from Alpha Centauri A can be estimated. Its brightness in the available filters can be extracted, though with uncertainty shaped by the brightness of the background and the difficulty of subtraction. Its statistical significance can be assessed relative to the noise in the surrounding image. Astronomers know that faint signals can look more persuasive than they are, especially when attention is focused on a scientifically valuable target. For this reason, they often ask how likely it is that a fluctuation of the background could mimic the observed feature, how stable the detection remains across independent reductions, and whether the source sits in a region of the detector known to behave cleanly. These tests do not eliminate ambiguity, but they begin to define its size. In the case of Alpha Centauri A, the candidate seems convincing enough to avoid immediate collapse under these questions. That alone makes it extraordinary. Around an ordinary star field, a faint source might invite modest curiosity. Around the nearest sun-like star, it instantly becomes one of the most watched points of light in modern astronomy. Yet the candidate's emergence is not only technical, it also changes the emotional structure of the search. Until this point, Alpha Centauri A remains a system of expectation, a place where planets may exist but none around the main star has clearly stepped forward in direct imaging. Once the source appears, even provisionally, that condition changes. Astronomers are no longer working only against absence. They're working against the possibility that something real has already shown itself and now demands explanation. The field around the star acquires a center of gravity. Follow-up plans become more urgent. Reanalysis becomes more intense. The faint point of light begins to gather meaning beyond its brightness. It is now the place where multiple futures branch. If the source is confirmed, it may become the first directly imaged planetary companion candidate around the nearest sun-like neighbour. If it fails, it will still teach a hard lesson about the edge of visibility in one of astronomy's most difficult searches. At this early stage, however, the image still permits wonder, restrained by method. The point of light sits within the processed darkness like a small defiance of expectation, not because astronomers thought planets impossible there, but because the observation itself is so hard that any surviving source seems almost improbable. It is the reward for all the prior layers of preparation, the infrared sensitivity, the coronagraphic suppression, the multiple roll angles, the subtraction of glare, the comparison across filters. Those methods do not produce a planet out of nothing. They make room for the possibility that a real one can be seen. And when a compact source remains in that room after the first rounds of scrutiny, the entire search changes character. Still, the source is only beginning its trial. Early tests can show that it is not obviously false, but they cannot yet show that it is truly planetary. For that, more must be learned. Its brightness must be interpreted physically. Its relation to the star must be considered dynamically. Its colour must be compared with expectations for a warm giant atmosphere, scattered dust, or background contamination. Most importantly, time must become part of the evidence. A real planet will not remain a static puzzle. It will move in orbit, or at least maintain a consistent existence that later observations can recover. For now, though, time has not yet spoken. There is only the first appearance, the initial stubbornness of the signal, and the cautious recognition that in the difficult light around Alpha Centauri A, something small has begun to stand apart from the glare. Once a candidate source survives the first stage of scrutiny, astronomy turns from detection to interpretation. The point of light near Alpha Centauri A is no longer treated merely as a stubborn feature in the image. It becomes an object with measurable properties, however uncertain, and those properties begin to guide the question of what it might be. The most immediate of these properties is brightness in the observed infrared bands. Brightness alone does not reveal the nature of an object, but when placed within a physical context it can suggest temperature, size, and possible composition. In the case of a nearby system whose distance is known with unusual precision, the apparent brightness of a source can be converted into an estimate of intrinsic luminosity, the actual amount of energy it emits. That is a powerful advantage. Around distant stars, uncertainties in distance can blur interpretation. Around Alpha Centauri A, distance is one of the least uncertain pieces of the puzzle. If the source truly belongs to the system, then its faint mid-infrared glow can be compared directly with theoretical models of planetary emission. This is where the candidate begins to resemble a giant planet rather than a random unresolved point. A warm gas giant does not shine like a star. It radiates a muted thermal glow shaped by internal heat, atmospheric structure, and the way energy escapes through clouds and gases. Even an old giant planet, long past formation, can still retain some residual warmth, especially if its atmosphere traps heat efficiently. In infrared wavelengths, this can place it just within the reach of a telescope like Webb, provided the surrounding starlight can be suppressed enough. The candidate near Alpha Centauri A appears faint, but not implausibly faint for such a body. Its measured emission suggests something cooler and less luminous than a star, yet potentially warmer or more detectable than a small rocky planet would be under the same conditions. This is what begins to draw the comparison with Saturn-mass worlds. The comparison does not mean the object would look like Saturn in visible light, with obvious rings and golden clouds. It means that the candidate's inferred brightness and likely temperature can be made broadly compatible with models of a gas giant whose mass lies in the range of Saturn rather than Jupiter or Earth. Mass itself is not measured directly from a single image. That is an important limitation. Direct imaging can show a source and estimate its luminosity, but converting luminosity into mass requires models, and models depend on assumptions. Age matters, atmospheric opacity matters, cloud layers matter, initial formation conditions matter. A young giant planet is much brighter than an old one because it is still cooling from its formation. A mature giant in an older system like Alpha Centauri would be dimmer and therefore harder to see, unless some other factor helps. The Alpha Centauri system is generally considered older than the solar system, or at least of comparable maturity, which makes a bright giant planet less expected than in young star systems, where direct imaging has often had more success. This age consideration is part of what makes the candidate so intriguing. If it is real, and if it is indeed a giant planet, then its detectability implies a balance of temperature, atmospheric properties, and observing wavelength that places it at a very interesting edge of visibility. The interpretation therefore grows from model comparison, rather than direct certainty. Astronomers take the observed flux, the measured energy in the relevant infrared band, and compare it with predicted spectra from giant planet atmospheres. These spectra depend on chemistry. Molecules such as methane, water vapor, ammonia, and carbon-bearing compounds influence which wavelengths escape more easily from the atmosphere. Cloud decks can either obscure deeper warm layers or irradiate energy in ways that alter the spectrum. A dusty atmosphere can behave differently from a clearer one. The resulting picture is complex, but it allows the candidate to be placed within a family of possibilities. It does not say, "This is Saturn." It says, "This level of brightness and this approximate colour could be consistent with a cool or moderately warm gas giant in the Saturn-mass range, depending on the assumptions." That distinction matters because astronomy at the edge of sensitivity must speak in conditional language. Even the temperature estimate is indirect. A thermal source seen in the mid-infrared can be assigned a brightness temperature, a value describing how much radiation it emits at a given wavelength, if it were approximated as a simple emitter. But real atmospheres are not simple emitters. Their spectra carry absorption bands, windows of transparency, and cloud effects that distort the relation between emitted light and physical temperature. Thus, the candidate's apparent warmth is best understood as a clue rather than a final measurement. It indicates that the object, if real and bound to the system, could be a self-luminous or weakly self-luminous giant with enough infrared emission to register against the background. From there, mass follows as an inference linked to evolutionary models of giant planets cooling over billions of years. A Saturn-mass interpretation becomes attractive because it balances the observed faintness with the need for an object large enough to produce measurable emission. A much smaller planet may be too dim. A much larger planet might be expected to appear differently, though model uncertainty leaves room for caution. Orbital distance also enters the interpretation. A source seen at a certain projected separation from Alpha Centauri A occupies a physical location that can be estimated from the system's known distance, though only in projection on the plane of the sky. The true orbit could be larger or differently inclined. Still, the candidate appears far enough from the star that a gas giant orbit is plausible within the known stable zones of the system. This strengthens the planetary reading. The object is not obviously in a place where orbital stability would be impossible. Instead, it seems to fall into a region where a giant companion could, under some conditions, persist over long timescales despite the presence of Alpha Centauri B farther away. All of these threads come together in a tentative portrait. The source is faint, localized, infrared visible, not immediately explained by a simple artifact, and situated where a giant planet could plausibly exist. Models of atmospheric emission do not reject such an interpretation. On the contrary, they give it form. The candidate begins to look like a possible warm gas giant, perhaps of roughly Saturn-like mass, orbiting the nearest Sun-like star. This is enough to transform a detection into a story, though not yet into a confirmed discovery. The uncertainty remains built into every parameter. The mass is estimated, not measured. The temperature is inferred, not directly sampled. The atmosphere is imagined through models, not yet observed in spectral detail. Still, the object now occupies a meaningful physical category. It is no longer merely a point, it is a possible world, described through heat, colour, and the disciplined language of probability. A giant planet around Alpha Centauri A would matter scientifically even if it were nothing like Earth, because giant planets shape the architecture of systems around them, and because their own physical nature can be rich, layered, and complex. Once the candidate source begins to resemble a Saturn-mass world in broad outline, the imagination of astronomy turns toward what such a planet might actually be like. This turn is not fantasy. It is an extension of comparative planetology, the practice of using known planets and physical models to infer the possible character of worlds not yet fully resolved. In the solar system, Saturn offers one reference point, a large planet made mostly of hydrogen and helium, with a smaller fraction of heavier elements, a deep atmosphere marked by banded clouds and storms, a powerful magnetic field, and a vast family of moons and rings. A giant planet around Alpha Centauri A would not need to duplicate Saturn in appearance or history to invite similar questions. Its atmosphere could be warmer or cooler, clearer or more clouded, richer or poorer in methane, shaped by different chemistry under the light of a slightly more luminous star. Its interior could hold a denser core or a different distribution of heavy material. Its weather could unfold on timescales unlike anything familiar in the solar system, yet the broad category remains useful. A Saturn-mass world is large enough to retain a deep gaseous envelope over billions of years. It is large enough to support layered cloud decks, strong winds, and thermal emission shaped by both absorbed starlight and internal heat. It is also large enough to influence neighbouring bodies, carving structure into any surrounding debris and shaping the orbits of possible moons. The concept of such a world around the nearest sun-like star carries an unusual kind of weight, because it would bring a giant planetary environment into the most local interstellar setting. If the candidate is real, it may not be the destination people first dream of, but it would become the first clear sign that Alpha Centauri A hosts a planetary system with complexity rather than emptiness. The atmosphere of a gas giant is not a single visible surface, but a deep column through which temperature, pressure, and chemistry change continuously with depth. What a telescope sees in infrared is usually not the solid body of a planet, because there is no solid body visible at the top, but radiation escaping from atmospheric layers where the gases become transparent enough for photons to leave. In such an atmosphere, clouds may form from compounds very different from the water clouds of Earth. Depending on temperature and pressure, condensates can include ammonia, ammonium compounds, sulfides, or deeper cloud layers of water. The exact balance would depend on how warm the planet is, how much stellar energy it receives, and how strong its internal heat flow remains after billions of years of cooling. Around Alpha Centauri A, a giant planet at a moderate orbital distance might receive somewhat more stellar energy than Saturn does from the Sun if its orbit lies relatively close. Yet this depends on the true separation, which remains uncertain when the orbit is not fully traced. Even so, a nearby giant planet in that environment might occupy an intermediate thermal state, shaped both by ancient retained heat and by a star slightly more luminous than the Sun. Such a balance could produce an atmosphere with moving cloud belts, long-lived vortices, and broad temperature gradients between equatorial and polar regions. The light Webb detects would be the outward whisper of that atmospheric structure, not a detailed weather map, but a faint thermal summary of deeper physical layers. The possibility of moons also becomes important. In the solar system, giant planets rarely exist alone. Jupiter and Saturn each host dozens of moons, including icy worlds with subsurface oceans, volcanic worlds reshaped by tides, and ancient cratered bodies preserving records of early history. A Saturn-mass planet around Alpha Centauri could likewise possess a system of satellites, though none are directly visible in the present evidence. Such moons would matter because they broaden the meaning of the planet. A gas giant is not only a world, it can also be a miniature planetary system. Large moons, if present, might experience tidal heating, eclipses, magnetic interactions, and climates unlike those of free-orbiting planets around stars. Some could, in principle, offer environments of astrobiological interest, especially if liquid water were maintained beneath ice or within complex chemical cycles. This possibility remains entirely speculative in the absence of direct evidence, but it helps explain why the discovery of a giant planet near Alpha Centauri A would be received as more than a single object. It would open the door to an unseen family of smaller worlds. Rings are another possibility. Saturn's rings dominate its appearance in visible light, but rings are not unique to Saturn, and their existence around another giant planet would depend on many factors, including collisions, tidal limits, moon formation history, and the long-term stability of icy or dusty material. A ring system around the Alpha Centauri candidate could alter its brightness and thermal properties in subtle ways, depending on orientation and composition. In principle, rings might even complicate interpretation by adding emission or reflected light not captured by simple planetary atmosphere models. Yet at this stage, such possibilities remain secondary. The main scientific significance lies in the giant planet itself as a marker of system formation. A planet of roughly Saturn mass implies a protoplanetary disk once substantial enough to build a core and accrete gas before the disk dispersed. It raises questions about whether the planet formed near its present location, or migrated there through interactions with a gas disk or with other planets. It suggests that the binary environment of Alpha Centauri A and B did not prevent giant planet formation altogether. That implication would reach far beyond this one world. It would influence how astronomers think about planet formation in nearby binary systems more generally. The imagined planet therefore lives at two scales at once. At one scale, it is a physical body, deep with clouds, layered with pressure, possibly ringed, perhaps orbited by moons, radiating a muted warmth into space. At the other scale, it is a structural clue, evidence that the nearest Sun-like star may have followed a planetary path not wholly unlike the Sun's own history. This dual importance is why even a tentative Saturn-mass world carries such force. It is concrete enough to picture and abstract enough to reshape theory. In the darkness around Alpha Centauri A, the candidate stands not merely as a possible giant planet, but as a possible organizing center of an unseen neighboring system. When the possible planet around Alpha Centauri A moves from internal analysis into broader scientific awareness, the response is shaped by more than the data alone. The reaction carries the weight of location, because discoveries around the nearest Sun-like star are never received as ordinary additions to a catalogue. They are received as changes to the local map of the universe. A candidate giant planet in such a system immediately attracts attention from astronomers working on exoplanets, planetary formation, infrared observations, stellar dynamics, and future mission concepts. It also reaches beyond the scientific community into public imagination, because Alpha Centauri has long occupied a singular place in cultural thought. It is one of the few stellar names widely recognized outside astronomy, a system that has become shorthand for the first destination beyond the solar system. Any suggestion of a planet there therefore travels quickly, not only because the evidence is interesting, but because the setting is already charged with meaning. In this stage of the story, the candidate begins to exist in two forms at once. It exists as a faint measured source in carefully processed infrared data, surrounded by uncertainty and technical discussion. At the same time, it exists as a narrative event, the possible appearance of a world around the nearest Sun-like star, a world that seems to step briefly out of abstraction and into public view. These two forms are connected but not identical. Science moves slowly and conditionally. Public excitement moves quickly and often favours the clearest version of a claim. The result is a tension that appears whenever difficult frontier observations seem to promise something historic. Astronomers understand this pattern well. They know that a candidate can be both scientifically important and still far from secure. Yet they also know that waiting for absolute certainty is not how research proceeds. Findings enter discussion because they are worth testing, not because they are already beyond dispute.
This massive
the candidate near Alpha Centauri A therefore becomes a focal point for careful announcement, skeptical reading, and widespread curiosity all at once. What drives so much of that reaction is the sense of proximity transformed into possibility. For years, the system has been a place of persistent searching with no comparably compelling directly imaged planetary signal around Alpha Centauri A itself. The appearance of this source changes that condition, even if only tentatively. The nearest familiar star begins to look inhabited by more than light. It begins to look planetary. That shift matters to researchers because it suggests that the long effort to probe the system may finally be touching something real. It matters to the public because it narrows the emotional distance between Earth and the rest of the galaxy. A world around a star many hundreds of light-years away can inspire awe. A world around Alpha Centauri invites a different feeling, quieter and more intimate. It feels closer to relevance, closer to eventual study, closer even to the far horizon of travel. This helps explain why the reaction to the candidate carries a kind of restrained astonishment. The possible object is not an Earth twin. It is not even presented as a habitable planet, yet its importance does not depend on that. The first confirmed giant planet around Alpha Centauri A would already transform the system from a target of search into a target of planetary science. It would immediately raise questions about other planets, debris structures, moon systems, and the formation history of the star. It would also sharpen interest in future observations with other facilities, both in space and on the ground. This is how discoveries in astronomy often work. One object becomes a gateway to an entire unseen architecture. Around Alpha Centauri, that gateway is especially compelling because the system is likely to remain one of the best observed stellar neighbours for decades to come. Scientific reaction also turns toward method. Researchers outside the original observing effort ask how strong the detection is, what reduction techniques were used, whether alternative explanations have been adequately considered, and what sort of follow-up would be decisive. This is not opposition in a simple sense. It is the natural response of a field trained to protect itself from premature certainty. A candidate this significant must be stressed from many sides. Independent reanalysis becomes valuable. The observing geometry is inspected closely. The brightness measurements are compared with theoretical expectations. Statistical significance is questioned not because the detection is unwelcome, but because it is so welcome that bias must be actively resisted. In this way, the scientific battle over reality does not begin as hostility. It begins as the routine, necessary pressure applied to any claim that seems capable of reshaping a major target of research. Around such a target, even optimism becomes disciplined. The wider reaction, however, is not governed by discipline alone. Alpha Centauri has long served as a symbolic threshold in science fiction, public education, and speculation about interstellar futures. The appearance of a planet there feels like a story humanity has been preparing itself to hear. That familiarity increases attention, but it can also distort expectations. A tentative candidate can be mistaken for a confirmed discovery. A giant planet can be spoken of as though it were already a destination for life. Astronomers must therefore communicate on two levels at once. They must preserve the uncertainty with technical honesty, while also acknowledging the legitimate excitement of the moment. This balancing act is one of the defining challenges of high-profile astronomy. The public is not wrong to care deeply about a possible planet around Alpha Centauri A. The care itself reflects the real importance of the system, but care can race ahead of proof, and in this case, proof still belongs to the future. Even so, the candidate's effect is real whether or not the source is ultimately confirmed. It alters observing priorities. It concentrates attention on follow-up. It encourages refinement of models for giant planets in old nearby systems. It stimulates debate about what direct imaging can and cannot yet deliver in the hardest bright star environments. It also reminds the field that the nearest stars are not exhausted subjects. They remain dynamic frontiers where new instruments can still change the landscape. For a time. Then. The candidate around Alpha Centauri A occupies a rare position. It is both a data point and an event. It belongs to the quiet technical world of image subtraction and infrared flux measurement, and at the same time to the much larger human story of looking outward for the first neighbouring worlds beyond the Sun. In that overlap, scientific caution and public wonder travel side by side. The source has not yet survived the full test of time, but it has already done enough to awaken the old dream in a new form. The nearest sun-like star may not be empty after all. For a moment, that possibility is enough to move the entire conversation. The turning point in the story arrives not with a brighter image or a stronger claim, but with absence. After the candidate source near Alpha Centauri A draws careful excitement and wider attention, follow-up observations become the essential next step. In astronomy, time is one of the strongest tests of reality. A real planet may move, but it should not simply cease to exist, even if its apparent position changes along an orbit. Later observations should recover it somewhere consistent with physical expectation, or at least detect a related signal that preserves the original interpretation. This is why the first return to the system carries such weight. The purpose of follow-up is not only confirmation in a ceremonial sense, it is the transition from plausible appearance to durable existence. Without that transition, even a well-behaved source remains fragile. Around Alpha Centauri A, the fragility of the candidate becomes clear when later observations fail to recover the object in the expected way. The point of light that seemed to persist through early tests is no longer plainly there. The prepared darkness around the star, once occupied by a possible neighbouring world, now appears emptied of that promise. This non-recovery does not automatically prove that the first signal was false, but it changes the balance of the case immediately and profoundly. The candidate moves from possible planet to possible vanishing planet, and that shift transforms both the scientific and emotional character of the story. A follow-up non-detection is one of the most unsettling outcomes astronomy can produce. A first detection can often be explained as a statistical fluctuation or a processing artifact if it is weak enough. But when that first detection occurs in a meaningful physical context and survives some initial tests, the failure to recover it later creates a more difficult landscape. The source was not obviously imaginary, yet now it is not obviously present. This is the space where scientific confidence fractures into competing interpretations. Some researchers begin by favouring the simplest explanation, that the original signal was not a planet after all, but a false positive generated by subtle structure in the data. Others consider whether the object could still be real but hidden, shifted, dimmed, or obscured in the later epoch. The missing source becomes a problem not only of observation, but of philosophy. What level of persistence must a signal show before reality is granted? And what kind of disappearance is still physically acceptable for a bound companion in such a system? The shock of the non-detection is intensified by the setting. If this were a faint candidate in a remote survey field, its loss might register as part of the ordinary difficulty of frontier astronomy. Around Alpha Centauri A, the same loss feels larger because so much significance had gathered around the possibility of a planet there. The nearest sun-like star had seemed, briefly, to offer a world. Now the image offers a silence where that world should have been. This silence is not empty, it is filled with implication. It suggests either that the original observation was misleading in some deep way, or that the physical interpretation of the system is more complicated than expected. Neither possibility is comfortable. The first threatens confidence in the detection itself. The second demands mechanisms that can reconcile presence and absence without breaking plausibility. Follow-up observations always have limitations of their own. Different instrument settings, wavelengths, roll angles, thermal states, and background conditions can affect what is detectable. A source near the edge of visibility in one epoch may not stand out as strongly in another if the observational circumstances are less favourable. This means the non-detection cannot be read naively. It is not equivalent to a declaration that nothing is there. Rather, it says that under the conditions of the later observations, the source is not recovered with the required strength or consistency. That nuance matters greatly, and it quickly becomes central to the debate. Was the follow-up sensitive enough to find the source if it remained similar to its first appearance? Was the expected position too uncertain? Could orbital motion have placed the object in a more difficult viewing geometry? Could the brightness have changed? These questions do not restore the candidate, but they complicate the meaning of its absence. Even so, the immediate effect on the community is unmistakable. Confidence drops. The tone of discussion changes from emerging discovery to unresolved anomaly. What had seemed like the opening of a neighbouring planetary chapter now begins to resemble a case study in the instability of marginal detections. Yet this change should not be mistaken for scientific failure. On the contrary, it is demonstration of science functioning exactly as it must. A claim is exposed to time, repetition, and independent testing. When the sky does not cooperate with expectation, the interpretation is forced to adapt. The emotional cost of that adaptation is real, especially in a case so charged with hope. But the methodological value is equally real. The missing planet becomes a harder and therefore more honest object of study than the original candidate had been. It now demands explanation across multiple epochs, not merely within one carefully reduced image set. The empty place in the later image acquires a paradoxical presence of its own. Astronomers begin to compare where the source was, where it should have been, and where the follow-up sensitivity should have allowed it to appear. They ask whether the absence is total or whether there are hints too weak to support recovery, but strong enough to resist dismissal. The field becomes one of close reading rather than simple sight. A non-detection near a bright star can still contain residual structure, low significance features, or ambiguous glimmers that prevent the story from settling cleanly into yes or no. This is part of what makes the missing candidate so haunting within the scientific record. It does not disappear into certainty, it disappears into argument. The nearest sun-like star seems, for a moment, to have revealed a giant planet, and then seems to retract it. That pattern is exactly what makes the case unforgettable. It is not merely that a planet may have been found and lost, it is that the loss itself becomes evidence, shaping every later attempt to decide what was really seen. In the prepared darkness around Alpha Centauri A, the empty region where the source once stood now carries nearly as much meaning as the source itself. The absence forces the field into its next phase, where simple excitement gives way to systematic doubt, and where the missing point of light begins to test the limits of both instrument and interpretation. Once the candidate near Alpha Centauri A fails to return in the expected way, the scientific response turns toward the simplest explanations first. This is not because simple explanations are always correct, but because astronomy learns most reliably by exhausting them before adopting more elaborate ones. The missing source must now be tested against a set of alternatives that do not require a real bound planet. The leading possibilities include instrumental artifacts, background objects, imperfect subtraction of starlight, detector noise, and structured dust emission. Each of these can, under the right conditions, create or preserve a compact feature in an image that resembles a physical source. The question is not whether such effects exist. They always exist at some level. The question is whether one of them can account for the original appearance of the candidate and its later disappearance without violating the details of the observations. This stage of inquiry is less dramatic than the first announcement and less emotionally vivid than the follow-up silence. But it is where the case becomes strongest in a scientific sense. The claim survives not by inspiring belief, but by withstanding alternatives that could have produced the same evidence more easily. The first alternative is an artifact of the optical system or the data reduction itself. Bright stars are dangerous subjects for imaging because their light produces intricate patterns across the detector. Even after coronagraphic suppression, residual starlight remains. Small mismatches in points spread function subtraction can leave bright knots, crescents, or isolated-looking peaks. If the observation is near the limit of what the instrument can cleanly separate, these residuals may take on deceptive shapes. A faint point that appears compact and persistent can still be the result of a subtraction process that has interacted with real optical structure in a misleading way. This possibility becomes especially attractive once the source is not recovered later, because a false positive produced by reduction would not be expected to repeat unless the conditions that created it were also repeated. Researchers therefore examine how the candidate behaves under different processing methods. If the signal weakens sharply when the subtraction model changes, or if its significance depends on a narrow set of choices, confidence erodes. Yet if it remains surprisingly stable across independent reductions, the artifact hypothesis becomes less comfortable. This is why the case does not collapse immediately even after the non-detection. The original source had shown enough persistence to resist being dismissed as a trivial blemish. Another possibility is that the source is a background object lying far behind Alpha Centauri A. In principle, a distant galaxy or other compact infrared source could happen to align near the star in projection. Because the Alpha Centauri system has a substantial proper motion across the sky, a background object should behave differently over time than a planet bound to the star. This makes repeated observations especially valuable. If the source were a fixed background object, the movement of Alpha Centauri relative to the background sky could eventually separate the two, or at least alter their apparent alignment in a predictable way. A background interpretation is attractive because it allows the original source to be real without requiring it to be planetary. Yet this explanation also faces challenges. The source appears in a region dominated by the bright nearby star, where extraction is difficult. A background object would need not only to be present, but to present the right brightness and compactness in the relevant infrared band. Depending on the exact field density of such sources, the chance alignment may or may not be likely. Statistical estimates become important here. If the background sky contains very few objects bright enough to mimic the candidate within the small searched area, the coincidence argument weakens. If such objects are common enough, it strengthens. The answer can depend sensitively on wavelength, depth, and the nature of the background population. Detector noise is another possibility, though usually a weaker one for a source that seemed to survive basic tests. Infrared detectors can show hot pixels, transient behavior, cosmic ray effects, and subtle correlated noise structures. Calibration pipelines are designed to identify and suppress these, but no system is flawless. A single noisy pixel rarely fools astronomers in a case like this, because the source should occupy more than one pixel in a way consistent with the optical profile of the telescope. Still, combinations of noise and subtraction residuals can create patterns more convincing than either would alone. This is often the danger at the edge of detectability. The false signal is not born from one dramatic flaw, but from the quiet alignment of several small ones. Dust within the Alpha Centauri system provides a more physically interesting alternative. Warm dust grains illuminated by the star can emit in the infrared and may produce clumps, arcs, or asymmetric structures if distributed unevenly. Such emission can be confused with a compact planetary source if the dust concentration is small enough and the resolution limited enough. A dust feature also offers a route to apparent variability. If the observed brightness depends on wavelength, geometry, or subtle changes in processing, the same underlying dust structure might look point-like in one epoch and less distinct in another. This makes circumstellar dust an especially useful explanation when a source appears plausible but unstable. It preserves the astrophysical reality of the emission while weakening the case for a planet. However, dust is not a free solution. The temperature, amount, and location of the dust must make sense within the system. The emission must also be compatible with what is known about debris disks and exozodiacal structures around sun-like stars. In some cases, dust can explain almost anything too easily if not constrained carefully. The testing of these alternatives becomes a process of elimination rather than immediate conclusion. Researchers compare the position and shape of the source with known instrumental features. They estimate the probability of a background interloper. They examine whether dust emission at the implied location would be stable, bright enough, and spectrally consistent. They revisit the noise properties of the detector and the image reduction. Each alternative gains strength from the non-detection because the burden on the planetary interpretation has increased, yet none may fully account for all aspects of the original appearance. This is what keeps the case alive. The simple explanations are compelling, but not always complete. The source seemed too organized to be shrugged away, yet too unstable to be trusted without reservation. In that tension, the scientific battle deepens. The missing planet becomes a contest between the comfort of the ordinary and the stubbornness of the anomalous. If a simple explanation wins cleanly, the story resolves into a lesson about caution. If none fits perfectly, uncertainty remains the honest outcome. At this stage, the field has not yet chosen a final answer. It is still moving through the disciplined habit of asking whether an apparent world can be reduced to light, noise, dust, and coincidence before it is granted the status of a planet.
This massive
The
gas
possibility that the candidate near Alpha Centauri A is real but intermittently hidden arises only after the simpler explanations fail to close the case completely. This is the stage where astronomy begins to test whether visibility and existence might have parted ways. A planet does not need to remain equally observable at every moment to be real. Its apparent brightness can change with orbital geometry, atmospheric conditions, phase angle, and the limitations of the instrument observing it. In a system as difficult as Alpha Centauri A, where the candidate already lies near the threshold of detectability, even modest physical changes or unfavourable viewing circumstances could move a genuine source below recovery. The challenge is to decide whether such hiding mechanisms are plausible enough to compete with the false positive explanation. For a giant planet, the first possibility is orbital motion. A planet does not sit still beside its star. It travels along an orbit that, depending on its size, eccentricity, and inclination, can alter both its projected separation on the sky and its visibility against the star's glare. If the candidate were observed at one point in its orbit when its apparent position placed it just outside the most difficult region of stellar contamination, a later observation might catch it closer to the star in projection, where the coronagraph and subtraction methods struggle more. In principle, this is a simple and respectable explanation. The problem is not whether orbital motion exists, but whether the motion required between the observation epochs is dynamically reasonable. A bound planet around Alpha Centauri A would move according to the mass of the star and its orbital distance. For a source seen at the projected separation suggested by the initial detection, the expected orbital period would still be measured in years rather than days. That means motion between two observations can be significant, but not arbitrary. The candidate cannot leap across the field. It can only trace the slow geometry allowed by gravity. Researchers therefore ask whether the follow-up observations would still have covered the plausible new position, and whether the source could have moved into a region of much lower detectability. This remains possible in some configurations, especially if the orbit is eccentric or highly inclined, but it is not a blanket solution. Orbital motion explains disappearance only if the disappearance occurs in the right direction and by the right amount. Another possibility is changing phase. A planet seen in reflected light can brighten or dim depending on how much of its illuminated hemisphere faces the observer, much as the moon changes phase in Earth's sky. In mid-infrared, where thermal emission matters more. Phase effects can still exist, but are generally less dramatic unless the atmosphere has strong temperature contrasts between day and night sides, or the observed wavelengths are sensitive to particular atmospheric layers. A warm gas giant might therefore vary somewhat with orbital configuration, yet the degree of change required to turn a marginal detection into a non-detection must be examined carefully. If the source is already interpreted mainly as thermal emission, rather than reflected light, phase alone may not provide enough variability to account for the missing planet. It can contribute, but perhaps not dominate. Atmospheric variability offers a subtler route. Giant planets are not static spheres of uniform glow. Their atmospheres can contain patchy clouds, temperature inhomogeneities, storms, and chemistry that changes with height and time. In some substellar objects, including brown dwarfs, measurable brightness variations occur as different atmospheric regions rotate in and out of view. A giant planet around Alpha Centauri E might likewise show variability if its atmosphere contains uneven cloud cover or dynamic circulation patterns. Depending on wavelength, these variations can be amplified or muted. In a marginal detection regime, even a moderate change in emitted flux might be enough to push the source below the threshold of recovery. This is one of the more intriguing possibilities, because it preserves the object as real while acknowledging that infrared brightness is not fixed. Yet here too there are limits. The source would need to vary by a meaningful amount, and that variability would need to occur on timescales that line up with the observation epochs. More importantly, the atmospheric variability must remain consistent with what is known about mature giant planets, rather than relying on extremes that are physically possible only in much hotter or younger objects. Dust offers another way for a real planet to hide. If there is local circumplanetary dust, a ring system, or intervening material within the Alpha Centauri system, the observed brightness could change as viewing angles shift. A dusty environment can scatter, absorb, or irradiate light in complicated ways. In one geometry, it might make a planet appear more prominent. In another, it might diminish or confuse the signal. Similarly, diffuse circumstellar dust near the line of sight might mask a genuine object during some observations more than others, particularly when the object lies close to the threshold of contrast. This class of explanation is attractive because dust is common in planetary systems, and because infrared observations are especially sensitive to thermal dust emission. But it also carries a danger. Dust can be invoked too flexibly, becoming a universal answer whenever a source behaves inconveniently. To remain persuasive, the dust must occupy a physically reasonable location, possess plausible temperature and grain properties, and affect the observations in a way that does not create new contradictions elsewhere in the data. Temporary obscuration by the planet's own environment is another speculative avenue. A giant planet might possess rings, extended material, or transient atmospheric phenomena that alter its observed brightness. For example, a ring system seen at one angle may present a different effective emitting area at another. Clouds could also reorganize under changing circulation patterns. These possibilities remind astronomers that a world is not a rigid dot, but a physical object with weather, geometry, and perhaps satellites or debris. Still, the evidence must guide the imagination, not the other way around. The more complicated the hiding mechanism becomes, the more it begins to resemble a rescue attempt rather than a naturally preferred explanation. This is why the real planet hypothesis remains alive but uneasy. It can accommodate disappearance through orbit, phase, atmospheric variation, or dust. Yet each mechanism demands conditions that must be checked against the actual timing and sensitivity of the observations. None is impossible, none is comfortably decisive. What makes the case scientifically valuable is precisely this friction between physical plausibility and evidential weakness. The source may have vanished because it was never a planet, or it may have vanished because the act of seeing a real planet in such a difficult system depends on a narrow alignment of circumstances that did not repeat. Astronomy cannot choose between these paths by elegance alone. It requires further evidence. And until that evidence arrives, the candidate remains suspended in a difficult but revealing truth. A world can exist without being visible, and visibility can occur without a world. Around Alpha Centauri A, the unresolved question is which of those two facts is the one the observations have actually encountered. As the case around Alpha Centauri A continues to unfold, the evidence no longer behaves like a clean discovery or a clean refutation. Instead, it settles into a more uncomfortable territory, where faint returns, marginal signals, and inconsistent recoveries begin to shape the debate. This is often the most difficult phase in observational astronomy, because it denies the comfort of a simple answer. A source that vanishes completely can sometimes be dismissed more easily than one that seems to flicker at the edge of significance. The latter resists closure. It leaves behind traces too suggestive to ignore and too weak to trust. In the Alpha Centauri case, later analyses and follow-up considerations bring attention to the possibility that something may still be present near the limit of detectability, though not with the strength or clarity required for confident confirmation. These low-level hints do not restore the original planetary interpretation, but they prevent the story from ending in a straightforward verdict of error. The result is a division not only over what the source is, but over how evidence near the threshold of visibility should be treated at all. A marginal signal is one that stands above the background just enough to attract notice, but not enough to dominate uncertainty. In such cases, the background itself becomes part of the argument. Noise is never featureless. Around a bright nearby star, the residual structures left after subtraction can contain ripples, asymmetries, and compact-looking fluctuations that mimic genuine objects. Yet not every compact fluctuation is meaningless. Some real astrophysical sources first appear exactly in this way, as low-significance features that only later grow stronger when more data are gathered or better methods are applied. The difficulty lies in telling the difference before certainty arrives. This is why the Alpha Centauri candidate begins to divide researchers into camps defined less by belief than by evidential temperament. One side sees the instability of the source across epochs as a warning that the original detection is probably an artifact or a non-planetary feature dressed in hopeful interpretation. The other side sees enough coherence in the original appearance and enough suggestive residue in later work to argue that the case remains open. Neither position is irrational. They differ mainly in how much weight they assign to non-repeatable signals at the frontier of instrumental performance. The later faint returns, where they are claimed or inferred, are not strong enough to settle the matter. They may appear as weak excesses near the expected region, small features that align imperfectly with the original candidate position, or patterns that become more interesting only after a certain reduction path is chosen. Such evidence is inherently unstable because it depends sensitively on processing assumptions. A slight change in subtraction strategy, alignment, or background estimation may raise the feature above notice or push it back into the statistical landscape. This sensitivity is exactly what makes the case so divisive. For astronomers trained to distrust signals that depend too strongly on methodological choice, these faint hints are a reason for caution. For astronomers more willing to consider that difficult real sources may only reveal themselves intermittently, the hints preserve the possibility that something physical remains in play. In both cases, the same data do not carry the same persuasive force. Threshold astronomy often behaves this way. The disagreement is not merely about the sky. It is also about standards of interpretation when the sky speaks softly. Statistical language becomes central here, though statistics alone rarely quiet the argument. Detection significance can be estimated by comparing the source brightness with the local noise properties of the image. But noise near bright stars is often non-Gaussian, meaning it does not behave as an ideal random background. Structured residuals, correlated pixels, and imperfect subtraction can all make formal significance values look more decisive than they really are. This is one reason why some researchers prefer empirical tests, such as injecting artificial sources into the data and asking whether the observed candidate behaves like something that could be robustly recovered. Others emphasize repeatability across epochs and reductions as the more trustworthy standard. In the Alpha Centauri debate, these methodological preferences matter greatly because the source never becomes strong enough to outrun them. If it were bright, the argument would shrink. Because it remains faint, the argument expands. The division also reflects a broader tension in exoplanet science between ambition and restraint. Direct imaging of planets around bright nearby stars is one of the hardest observational tasks in the field. Progress often comes through small gains, improved processing, and the willingness to examine data at their limits. If astronomers set the bar so high that only overwhelming signals count as meaningful, some real phenomena may be overlooked for years. If they set it too low, the literature becomes crowded with ghosts of noise and optimism. The Alpha Centauri candidate sits exactly on this fault line. It is scientifically valuable, partly because it forces the field to confront how it wants to behave at the edge. Should a tantalizing but unstable source around the most important nearby target be held in suspension as an unresolved possibility? Or should the burden of proof be considered unmet until strong repeatability appears? Different teams answer differently, and those answers reveal something about the evolving culture of high-contrast exoplanet work. The candidate's faint reappearances, if they are real reappearances, also raise the possibility that the system itself is more variable than a simple planet model assumes. Dust, atmospheric modulation, orbital projection, and changing observing conditions may all contribute to an intermittent observational footprint. Yet every added complexity cuts both ways. It can make a genuine source easier to hide, but it can also make a non-planetary interpretation easier to sustain. In this sense, the case becomes self-entangling. Each attempt to save the planet hypothesis by invoking variability or geometry also enlarges the space of ambiguity. Each attempt to dismiss the source as noise must still account for why the original candidate seemed so well placed, and why later traces, however weak, continue to invite attention. The debate therefore persists not because the evidence is strong, but because it is just strong enough to resist erasure. Around Alpha Centauri A, the candidate has become less like a discovered planet and more like a recurring question written in faint infrared light. It appears, fades, perhaps flickers, and in doing so exposes the narrow boundary between detection and interpretation. Some researchers see the boundary and step back, others see it and lean in. The divide between them is not merely disagreement, it is the natural consequence of trying to extract meaning from signals that live at the very edge of what current instruments can honestly say. What the unresolved case around Alpha Centauri A changes is not simply the status of one candidate source, but the way astronomers think about nearby planetary searches at the edge of visibility. In science, an unsolved observation can be as influential as a confirmed discovery if it reveals where methods succeed, where they fail, and where reality may be more complicated than instruments are prepared to show. The possible vanishing planet enters this category. Whether the original source proves to have been a real giant world, a dust structure, a background interloper, or an especially persuasive artifact. The case has already altered the conversation about what it means to search for planets around the nearest Sun-like stars. It has shown that the problem is no longer one of simple absence. The field has moved beyond asking whether such a search is worth attempting. It is now confronting the more difficult question of how to interpret faint, unstable, and physically suggestive signals in systems that matter enormously. This is a sign of progress, though not a comfortable one. Astronomy advances not only through decisive yes answers, but through better defined uncertainty. The Alpha Centauri mystery refines uncertainty into something highly productive. It exposes the narrowness of the observational window through which a nearby giant planet might be seen. It reveals how dependent direct imaging remains on subtraction methods, calibration quality, wavelength choice, and repeat observations across time. It also reminds the field that a bright nearby star is not an easier target simply because it is close. In some respects it is harder, because its nearness and brilliance demand a level of optical control that pushes current instruments into their most vulnerable regime. That lesson will shape future searches. Every next campaign around Alpha Centauri A will be designed with greater caution, better simulations, and more explicit sensitivity to dust, variability, and statistical false positives. The mystery therefore becomes a training ground for the future of direct imaging. It teaches astronomers how to build cases that can survive disappointment and how to recognize when an apparent world has not yet earned the stability required for belief. At the same time, the case preserves the possibility that nature is more elusive than simple confirmation standards assume. A real planet does not become unreal because it is difficult to recover. Complex atmospheres vary. Dust can mask. Orbital geometry can conspire with glare. Systems near the threshold of detectability may reveal themselves only intermittently until better instruments arrive. This is why the Alpha Centauri candidate continues to matter even without resolution. It lives in the gap between what current data can establish and what future data may clarify. That gap is where many important astronomical transitions occur. The first hints of exoplanets, disks, and black holes often pass through periods of doubt before the instruments improved enough to decide the matter. The current mystery may yet follow that pattern, or it may eventually dissolve into a cautionary example of how compelling noise can become near a beloved target. Either outcome would be valuable if the candidate is real. Then the nearest Sun-like star may already have offered the first glimpse of a neighbouring giant world, one whose fleeting visibility says as much about observational difficulty as about the planet itself. If the candidate is not real, then astronomy has still gained a clearer understanding of the false structures that can arise in the hardest high-contrast infrared observations. The search around Alpha Centauri A will continue either way, because the system remains too important to ignore. Its nearness still makes it the natural focus for future observatories, larger ground-based telescopes with advanced adaptive optics, more refined coronagraphs, and perhaps one day dedicated missions designed to suppress starlight far more completely than is now possible. In that longer view, the vanishing planet may become an early chapter in a much larger story. It may be remembered as the first ambiguous sign before a later confirmed census of the system, or it may stand as the moment when astronomers learned exactly how deceptive the threshold around Alpha Centauri can be. What endures now is the deeper meaning of the case. Science is often imagined as a steady replacement of ignorance with certainty, but in practice it more often advances by making the unknown more precise. The Alpha Centauri mystery has done exactly that. It has narrowed the space of argument. It has forced theories of nearby giant planets, dust environments, and observational limits into direct contact with one another. It has shown that the first interstellar destination in the human imagination is not merely a passive point of hope, but an active scientific frontier where evidence must be earned under extreme conditions. This is why the case matters beyond its own unresolved status. It changes the emotional balance of the search. Before the candidate appeared, Alpha Centauri A was primarily a place of expectation. After the candidate appeared and then seemed to vanish, the system became something else, a place of contested evidence, of disciplined longing, of science working at the exact boundary where hope is strongest and proof is weakest. That boundary is not a failure. It is where astronomy becomes most honest. A nearby world may be there, hidden in geometry, heat, and glare. Or the world may exist only in the temporary alignment of noise and desire. For now, the truth remains suspended between these possibilities. Yet even in suspension, the case has altered the map. It has made the nearest stellar neighbour feel less silent, less settled, and more alive with unanswered structure. For humanity's first imagined interstellar destination, that may be the most consequential outcome of all. The search has not ended in certainty. It has ended in a more demanding form of attention, and that attention will shape every future attempt to find what truly moves in the light of Alpha Centauri A.